A lot of the theorems we worked with previously depend on the results that we cover in this video. The mean value theorem is used to prove a lot of the theorems like the Fermat's theorem, which is about maxima, local maxima and minima, the first derivative test, and so forth. But before we can jump into the mean value theorem, we have to look at a preliminary result, which is called Rolle's theorem. So Rolle's theorem is about a function that has to have three properties. One, the function f has to be continuous on the closed interval AB. Two, the function has to be differentiable on the open interval AB. And three, the y value at the left endpoint, f of a, has to be equal to the y value at the right endpoint, f of b. If these three conditions are satisfied for some function f, so f is a function, let's see what happens. Then, well, before I write the result, let's see if we can draw a diagram here of such a function. So I'll start by putting the interval AB. And so whatever the value is at a, let's say the y value is here somewhere. This is f of a. It should also be f of b. So if I trace that down here, okay, it's also f of b. So this function can do whatever it wants. Let's draw a better one. This function can do whatever it wants. It's continuous on the interval and it's differentiable on the interval, open interval, okay? Then the theorem says there is at least one point on the graph that has a horizontal tangent line. There could be more than one, like in this case there's more than one. But the theorem says there's at least one number c between a and b where the derivative of the function at that point is 0. Okay, so the function definitely has a horizontal tangent somewhere. That's what the theorem is saying. So then f prime of c is equal to 0 for at least 1c in AB. Or I should be clear here, in the open interval AB. Okay. So first let's see what might happen if these three conditions are not satisfied. If one of them, we need all three of them. Okay, if one of them is not satisfied, then we might have a problem. So let's take a look at an example. So I'm going to call this a non-example because it doesn't work. So here's the xy plane. So I'm going to draw a graph of a function that satisfies the last condition. So f of a will be equal to f of b. And the function's going to be smooth everywhere, so it's going to be differentiable, but it's not going to have continuity at the endpoints. So here's an example of a function where if this is a and this is b, so f of a equals f of b. So the third property is satisfied. And then f is differentiable on the open interval AB. So the second condition is satisfied. But f is not continuous at the endpoints. So the first condition is not satisfied. And you can see there's no value of C there's no value, or there's no location where there's a horizontal tangent line. Okay, so the first condition is necessary. Let's do another non-example. So here's another non-example. In this non-example, we're going to build a function that satisfies the first condition, so it's continuous throughout the interval, including the endpoints, and the left endpoint and the right endpoint have the same y value, so f of a equals f of b, but the second condition, which is the differentiability, is not going to be satisfied. So let's build such a function and see what the problem might be if this happens. So, okay, here's f of a and here's f of b. They have the same y value. Okay, and the function is continuous at the endpoint, so I'll do this. But I'm going to kill the differentiability option at this point. So as you can see here, f prime does not exist at that point. Okay, and so here there's no value, or there's no location on the graph that has a horizontal tangent line, because actually the only candidate, which is that sharp point, is not differentiable there. So we definitely need the second condition. Okay, and then let's do one more non-example. Here's another non-example. In this one, I'm going to make sure the function is continuous throughout the interval, including the endpoints. It's differentiable on the open interval, but f of a is not equal to f of b. Okay, so let's take a look at that example. So here is f of a, and then f of b, I want it to be different y value. Okay, so here's an example of a function that's continuous throughout the interval. It's differentiable everywhere, but f of a is not equal to f of b, and so you can see there is no value, there is no location that has a horizontal tangent line. So to understand this theorem really well, you have to understand why each of these conditions are necessary for you to guarantee that there's at least one place that has a horizontal tangent line. Okay? And that, of course, we call that a critical number, which we studied earlier to find local maxes and mins.